All right, we are back. And we are ready to start with chapter 28. So we said that we have these two chapters on magnetic forces and magnetic fields. And now we're moving on into chapter 28. And chapter 28 is looking at the magnetic fields. And it's primarily answering the question, how do we configure, how do we generate a magnetic field? And that's going to be the topic for the chapter here. Now, we actually, in chapter 27, we did look at some examples of how magnetic fields get generated. So it's not like we haven't looked at this at all. And the first thing that we want to start off with is kind of the same picture, one of the same pictures we had from chapter 27, is if I have a current traveling through a wire, if I have a current of charges, a bunch of charges that are in motion, I'm going to end up with looping magnetic field lines around the wire. And what's nice about this particular magnetic field shape is it's pretty simple. Now, in order to have this formula, we got a formula right here. We're going to start talking about how that gets derived. This is near a long straight wire. So this is coming back to some of those approximations that we saw with Gauss's law. The idea is that this formula for the magnetic field around a wire is going to work pretty well as long as we're close enough to the wire that from where we're standing, it looks like the wire just goes on and on and on. So if I'm standing in this region in here, maybe I can see the wire seems to go off into infinity. But once I get far enough away from the wire, I can look at it and go, it doesn't look infinitely long from here. And so the formulas that we come up with are going to work well as long as we're in that region where we're reasonably close to the wire compared with how long it is. Now, the formula that they've come up with is the magnetic field depends on the current, so it's directly proportional. As we get more and more current, the magnetic field gets larger. And then it depends on distance. And so for a long wire, the magnetic field actually drops off like R. Now, in the previous chapter, in the previous lecture, actually this isn't in the book, but in the previous lecture we talked about using point charges instead. So we said rather than start off with a long wire, let's just start off with individual charges. When we look at an individual charge, we don't get this 1 over r dependence. We get 1 over r squared, which is like the electric field. Anyway, when we look at an entire wire of current in terms of magnetic field, it's kind of like saying, well, what's the electric field due to a stick of charge? So, and as you guys know from chapter 21, calculating the electric field around a length of charge isn't the same thing as doing an individual point charge. So for right now, let's go ahead and think in terms of this formula. Now they've moved on and they're using a different constant. Instead of using little k, which we've been using throughout, they're going to start using this constant mu naught divided by 2 pi. Now it says here that mu naught actually is exactly 4 pi times 10 to the minus 7 Tesla meters divided by amps. I'm going to keep using little k, but what we'll do is we'll look and see where mu naught comes from and see how that gets defined. We don't need a new force constant. Everything that happens with electric or magnetic forces is all due to just one force of nature. So we only need one force constant to keep track of that. All right, but let's get some practice with calculating magnetic fields then. How large will the magnetic field be due to current running along a wire? I'm going to step 10 centimeters away from that and pick a point. This is point P. I kind of missed my point A, but this is point P. let's see. I do have to make sure that, at least with the formula we're working with so far, that the wire is much longer than 10 centimeters. So if I'm going to pick a point 10 centimeter, you know, the wire's here and I'm looking at a point over here, that wire needs to go on for a good length in order for this to be a reasonable calculation. But what it says is this. It says that the wire is carrying a current of 25 amps, and we're looking at a point 10 centimeters away. Doesn't sound like too many numbers that we need to have to carry out this calculation. So here is, well, I'm going to go back. So I'm going to go back to a point charge and say, wait, before we do something really complicated like current going through a wire, what I want to do is get a feel for what the individual charges are creating. And again, I'm going to go back and remind myself that an individual charge, in general, will have both an electric and a magnetic field to it. Now, the magnetic components depend on the charge being in motion. So if the charge is at rest, that means it's not spinning, it's not an electron or a proton. It's a charge, it's just sitting there at rest, no spinning, no velocity. Then it will only have the electric components. But if it is moving, it will have the magnetic components. Now that raises a bit of a paradox here, because let's say that I'm driving along in my car, and everywhere I go, I always take my 2 electric charges with me. Now, I've got these 2 electric charges set up, maybe they're on my dashboard, and I'm driving along, and I'm looking over, in my reference frame, those charges are at rest. And for those charges, I only observe them to have an electric field. But what happens with somebody outside watching me go by? So if someone outside is watching me go by, I'm zipping along in my car, and they look, and what they do is they see these charges moving past them. And they're going, those charges are generating magnetic fields. And sure enough, in their reference frame, the charges would have both electric and magnetic field components. And that's why I use the word component. It turns out that the electric field is represented as a vector. It's got 3 components, Ex, Ey, and Ez. Magnetic fields also we're representing them as vectors. They have components Bx, By, and Bz. It turns out that there are really 6 components of the same object. So the 3 components of the electric field and 3 components of the magnetic field actually make up what's called a tensor. Now, tensors look like matrices. So the electric and the magnetic field components, that's how I'm going to refer to them, are actually coming off the same mathematical structure. And what is purely an electric field in one reference frame will have different components in another reference frame. So anyway, and that's why I keep trying to draw emphasize these similarities to where electric and magnetic fields, well, they both have factors of kq over r squared. That's common to both. In order to correct for the historical fact that we use different units, I have to put an extra factor of c on my magnetic fields. The magnetic fields are going to depend on the velocity, and that velocity is going to be a ratio, v is to c, and then the directions are different, and the direction of the magnetic field will introduce a factor of sine theta. So if I have a charge moving along with velocity v in this diagram, it's moving, I should write in a v here, it's going to have an electric field, and the electric field will be in that direction. It's going to be in the direction of that radial unit vector. But the magnetic field is going to be given by this lower formula, and that is going to be in the direction of velocity cross radial. I have to take the cross product of those 2 unit vectors. And so when I take the cross product, that gives me something coming out of the board. So this is my starting point. Again, it's not in the book, but it's an individual point charge. And what we've been able to show or claim is that it has a magnitude of kq over c squared v divided by r squared times the sine of theta. So that tells us for an individual point charge how much magnetic field will be generated. Now if all I have is this one point charge, then its field kind of follows it where it goes. So if I take any snapshot of that charge's magnetic field, it actually is spread out around the charge. And as long as the charge isn't moving too fast, that's the formula that we have for it. Now, right here, I put a little subscript V, and what I'm saying is this is actually the magnetic field for a charge based on its velocity. But if the object is also undergoing an acceleration, there's another term that we have to add on. We'll start to see that in chapter 39, or chapter 29, sorry. We're not doing chapter 39 in this course. We'll see that starting kind of in chapter 29, 30, and 31, in those later chapters. We're going to bring in the acceleration effects. But for right now, we're just looking at what is the magnetic field specifically due to the charge's velocity. So I put that in here, but I'm going to drop it. I'm not going to keep it in the rest of the examples. But everything we do in this chapter is going to be based on purely what we call the velocity fields for the electric and magnetic effects. All right, now if that's a charge, and this is its fundamental equation saying how large the field is going to be, what that says is the field drops off with distance, gets less and less as we get farther away, and it drops off like 1 over r squared, same as the electric field. But it also has an angular dependence. And by angular dependence, it's saying, hey, oh, there is a v there, right? So the v is in this direction. If the v is in this direction, then I can measure theta relative to the direction of motion. So wherever that charge is headed, straight out ahead is at 0 degrees, straight behind it is at 180, and then here are all the sideways directions in here. And what that sine theta factor is telling me is that straight out ahead, the magnetic field is 0. So the field is actually 0 out ahead of this charge. The field is also 0 right behind the charge. But if I look in sideways directions, the field actually gets largest at 90 degrees. So as this charge goes by, the largest values of the field are out sideways. And then we said that the field propagates out. There's a time delay for the field and how that happens. And we said that the field actually, even though there's a time delay, because of relativity effects, the field actually keeps up with the charge. The field doesn't get left behind for velocity fields. So the field, the shape of the field, stays caught up right with the charge as it's moving through space. Kind of an interesting effect on that too. All right, so spend some time thinking about how that works. Now what we can do is, instead of looking at individual charges, we can move on and ask, well, what would the field look like for a current? For current running through a wire, what would the field, because we can build those. This is kind of tricky, building a beam of charged particles, but anytime I have a wire with current going through it, it's kind of like a beam of charged particles contained within that wire. And so there's a whole bunch of charged particles inside here, all in motion. They make up the current. And I can take information from here and apply it to here. First thing I want to look at is, well, what's the direction then? What's going on with the direction of the magnetic field? What we saw for the direction of the magnetic field was this. We saw that in this section, kind of above where this charge is located on this diagram, the field is coming out of the page. And then down below here, using the cross product, it's going into the page. And what's really happening here is, here's the charge moving in this direction. And what's happening is I have magnetic fields that are oriented in a way where if I follow those magnetic fields, they form circular loops around the path that the charge is following. So whatever path the charge is following, that's going to be kind of the center line for these circular loops of magnetic field. Now with an individual charge then, what that means is everywhere up here the field's coming out of the board, but it's not uniform. Remember, it drops off with r squared and it depends on angle. Now if I take a bunch of charges, then what I can say is I'm still going to get that looping effect. I'm going to have magnetic fields coming out of the page and then going back in. Magnetic fields coming out of the page, going back in, and then looping around back behind. Now, it's important to remember here, there's nothing moving. When we draw these arrows for the electric and the magnetic field, it's not like there's things moving away from the charge or around the charge. It's just the orientation. It's like a bunch of one-way signs. So I've got a bunch of one-way signs here. Here are all these little arrows. The signs themselves are not moving. They just, when I look at the completed set of signs, it's a path. It's a series of directions, and it says, if I'm right here, that's how the magnetic field is oriented. If I'm here, that's how the magnetic field is oriented. If I'm here, that's how the magnetic field is oriented. So for a wire, what we end up with are these circular paths of magnetic field lines. And so I got the X's and the O's back. The O's are where the field's coming out of the page. The X's are where it's going back into the page. And what we can do then is, as we start to see examples, we can kind of take that diagram, get some scissors, cut it out, and rotate it around as needed for the particular example we're encountering. All right, now how do I get from individual charges to here? And I'm hoping what you're all guessing is that, that would be some kind of an integration, and it is. So we'll see how that works. What we can do is start from here, carry out an integration so that it's not just one charge, but it's a whole series of charges, and create a current. Now, for now, I'm just going to write down the formula. So the formula we have for the magnetic field surrounding a wire with current, a long wire with current passing through it, when we carry out that integration, it turns out to be 2ki over c squared times 1 over r. So that's kind of important too. Individual charges, the magnetic fields drop off like 1 over r squared, same as an E field. So E fields or B fields for a point charge have a 1 over r squared dependence. It's only when we integrate this out to get the current that we end up with 1 over r behavior. Now that's the formula I'm going to use. The formula that the book gave us was this, if you remember back on that previous slide. They had a formula that had this mu naught over 2 pi. Let's see how that matches up. Well, this mu naught that they're starting to use is a factor of 4 pi k over c squared. So it does turn out that mu naught, it's just a different version of k. It's directly proportional to k. What they've done is they've added in a 4 pi over c squared, which is going to make some formulas simpler, but it's going to make other formulas more complicated. So you guys can judge for yourselves, like in this example, which formula is easier. And then, of course, my bias always is, even if that were to make it easier, I don't want to use that because it might make me start thinking that there's a different magnetic force constant compared with electric, and that's not true. Everything can be done in terms of one force constant. So with this definition, or with this formula here, that is the formula that defines mu naught, you can always switch back and forth between the two. So textbook's going to be using mu naught. In my lectures, I'm going to stick with K. So you'll see both in the lectures. When I'm using the textbook slides, there will be a mu naught. All right, so I'm using that very same, there it is. There's the formula right there. So here's the formula that we had written down for the magnetic field surrounding a wire with current running through it. So here's my wire. Here's point A, because I drew this one. So the points are labeled A, and I want to figure a distance. Now the distance I want is not from the surface of the wire. I want to get something measured to the center of the effect. So the distance here is going to be measured from the center of the wire out to where point A is located. And plugging everything into this formula, just a reminder, the electric magnetic force constant, little k, 8.99, 10 to the 9th newtons meters squared over coulomb squared. Let's imagine that we have a current of 25 amps. I do have to start thinking in terms of factors of C. So I'm going to start using, factors of C are going to start showing up in the examples that I'm working with. And so I'm going to put a factor of C in because I got a factor of C here. One thing to keep in mind here is that, like, the significant figures here are 8.99 something. Significant figures here are like 2.998. It does turn out that the way that the coulomb is defined, that the K over C squared, the 9 that we have here, exactly cancels the 3 squared. So even though the sig figs look like they don't quite match up, they match exactly. And it's actually built in to our definition of the Coulomb. So if you're doing calculations this way, if you're using the formulas that I'm writing down, whenever you see K over C squared, go ahead and use 9 times 10 to the 9th for K, because that 9 will exactly cancel the 3 squared that you're putting in for C squared. Okay, so 9 divided by 3 squared, that just goes away. In fact, you could just put in 1 times 10 to the 9th, divide through by 10 to the 16. That's always going to become 10 to the minus 7. Okay, it's a bit of a shortcut. I wouldn't advise doing it until you're familiar, until you've done the calculation so many times, you thoroughly understand what's going on. And then the last thing we had to do was tell someone, how far are we away from the center of the wire? So we had measured from the center of the wire out to this location, and we're getting 10 centimeters for that. All right, magnetic field that I calculated using that formula. I hope I got it right. Again, you can check all the numbers on these. The magnetic field that I ended up with was 50 micro Tesla. And that's to be expected. We don't generate enormous magnetic fields with these wires. Now, this is the magnetic field magnitude. What's the direction? What direction is the magnetic field in? And what we've got here is we've got magnetic field loops around this wire. And so I'm going to have magnetic fields into the page on this side, coming out of the page here, and then if I follow those orientations, again, if it's a series of one-way signs, they go back behind and then they loop back out again. So I'm just going to draw a bunch of O's and X's. O's and X's are good. I can see what the orientation is going to be from that. Now, one last thing that I did here is, I'm always feeling like, since electric and magnetic field components are given different units, it's kind of hard to compare. It's kind of like if we measured horizontal distances in meters, but we measured vertical distances in feet, and no one was allowed to use, those were just 2 different units. And someone came along and said, but wait, there's just an easy conversion. if we want to take a magnetic field calculation and compare it with an electric field, the way we would do that is just multiply by C. Once we multiply by C, we end up in the same units with both. And if you see, look at the formulas, you'll see the formulas match up. So a 50 microtesla magnetic field would be equivalent to 15,000 newtons per coulomb. And then it doesn't seem so small anymore, right? 15,000 newtons per coulomb, that was a pretty good sized electric field. Well, that's the equivalent calculation for a magnetic field of 50 microtesla. All right. All right, let's try another example here. What we're going to look at is magnetic field due to, well, we're still looking at magnetic fields due to straight wires. This time we have two wires. So rather than just calculating one magnetic field, we've got one wire traveling with its current coming out of the page here, out of the board. And then we got another wire with current going in this direction. And the currents don't match. So they actually gave us this problem. They say that wire number 1 is carrying a current of 5 amps, and wire number 2 is carrying a current of 7 amps. So they're not connected. They're not the same circuit. There's different amounts of current here. The wires themselves are separated by 10 centimeters, so here's the two wires, and I guess the currents are going some direction. What would the magnetic field be halfway between? So if I pick a point right in between those two wires with current going in opposite directions, what would the magnetic field be? Now to carry out that calculation, I'm going to say we want to do direction first and magnitude later. So let's get the direction figured out. See this picture right here? And then there was a picture before that too. That one. So if we go all the way back to here, remember our point charge and how we determine directions, velocity cross R. What we find for currents traveling through wires is that, here's a right-hand rule which I think actually is pretty useful. If I put my thumb in the direction of the current, my fingers kind of curve in the direction of the magnetic field. So something with current in that direction, you're going to get magnetic fields that loop in a right-handed direction. That's the same thing we used in this example. Here is my thumb in the direction of the current, and my fingers are looping on my right hand. Fingers are looping back behind and out front of that wire, and that's a quick way to remind myself what direction it would be. Now, in this case, I have wires going out of the page and into the page. How do I use that? And I can do the same thing. I can say, hey, my thumb for current number 1, that's coming out of the page. And that means I want my fingers wrapped in a direction where the magnetic fields circulate in that direction. And that's how they've got those arrows set up. Now for current number 2 then, I've got my fingers wrapped around, my thumb is into the board to show the direction of current, and then my fingers wrap around. Now when I look at a point halfway in between, what I realize is, oh, those two magnetic fields are pointing in the same direction. I'm getting two distinct contributions to the magnetic field at that midpoint, and they're both pointing in the same direction. That means I don't have to do vector addition. Okay. Now, if they had picked almost any other point, a point over here or something, then I could have, you know, magnetic fields pointing off in different directions, and I would have to break that into components and figure out what the magnetic field is. But for this example, I know the direction of the net magnetic field already. The net magnetic field is up. And to calculate the magnitude, I just add the magnitudes of B1 and B2 together. Now, yeah, I think we already looked at the numbers on there. All right, here's the problem set up. So we've already determined directions. We know that B1 and B2 are going to add together, and they're going to be at point A. The magnetic field will be in that direction. So another reminder, with all these vector diagrams, everything going on with the vector only applies to the point, to one location in space. This B1 and B2 doesn't apply to anything up here. It only applies to what the value of the magnetic field. It's easy with vectors. Vectors are such handy notation, drawing little arrows for things. But we do have to remember that those arrows don't represent anything other than properties measured at one location in space. Okay. Here's what seem to be the relevant numbers. So what we would need to know then to carry out this calculation is how much current do I have in each one of the wires, and that was given, and then how much distance is there from each of the wires back to that midpoint. And we were told that each of those was 5 centimeters. So we know the R's, we know the currents, and I can now plug into my formulas. Now remember, these formulas are for long straight wires with current running through them. And so I can plug into my 2K over C squared times I1, 2K over C squared I2, and then divide through by 1 over R1, 1 over R2. The higher current, the 5 amps at 5 centimeters out, gave me 20 microtesla. The 7 amps at 5 centimeters out gave me 28 microtesla. So I ended up being able to calculate what those values are, and since the two vectors line right up at point A, I can just add those numbers together. So I'm getting 48 microtesla as the combined magnetic field at point A. Questions on any of that? Worth pausing here for a minute, see how all those numbers come together. All right. Here's one that's a little trickier. I don't think we're gonna, in fact, I don't think they necessarily give numbers here. Oh, they're just asking what are the magnetic fields like? So let's say that we have 4 wires now. So I've got 2 wires with current going into the board, and I got 2 wires with current coming out of the board. In the first diagram, it says that each wire carries the same amount of current, and that the point at the center, the pattern of wires make up a square, and so a point right at the center is the same distance away from each one. Now, going back and looking at my formula, going back and looking at a formula for the magnetic field surrounding a wire says, hey, if I got a bunch of wires and they all have the same current, and I have found a point that's the same distance from each of the wires, they should all be creating the same magnitude of magnetic field. And that's what we've got here. Since it's a point right in the middle, the magnetic field magnitude from each of these will match. So it really comes down to identifying the direction of the magnetic field due to each wire, and then determining, once we've got the direction figured out, adding those vectors together. So let's see how the right-hand rule would work here. What we're going to end up with is, for currents 1 and 2, they're going into the board. So I can take my thumb, point it into the board, and then wrap my fingers around. Now what I'm specifically looking at is point A right in the middle. And so if I'm wrapping my fingers around, what that's going to give me at point A is something pointing in that direction. And again, the direction of that arrow is only referring to what is the magnetic field at that one point in the center. All right, so that's creating a magnetic field here. If I do the same for current number 2, wrap my fingers around, what that says is if I curve around here, I'm going to be pointing in that direction, the direction that has a 2 labeled on it. So currents 1 and 2 are going to produce magnetic fields oriented in the directions 1 and 2 on the diagram. Now if I come down to 3 and 4, now I've got currents coming out of the board, and so these are going to be curved in the other direction. So if my thumb's coming out here, I'm curving fingers around, that means at that point the magnetic field is oriented in that direction. And then when we carry out the calculation for 4, the direction for 4 lines up with the direction of 1. All right, how large? Where is the net magnetic field? And since the net magnetic field will be the vector addition of those 4 magnetic field contributions, I have to do vector addition. Now each one of those is equal in magnitude, and so what I can see is that 2 and 3 line right up at 45 degrees in that direction. 1 and 4 line right up at 45 degrees there. Hey, if I add those together, I'm going to get something exactly in the horizontal direction. So combined, the sideways components are going to cancel out. The horizontal components are going to add together, and I'm going to get 4 of those. So that's the direction it's going to be in. Now, in the second picture here, what they've done is they've reoriented a couple of those wires. So let's see how those wires have been reoriented. 2 has been reversed, and 4. So 2 and 4 now are reversed, and without going in and redoing all of the right-hand rule stuff, what that's going to do is reverse the direction on 2 and reverse the direction on. So 4 is going to be pointing in that direction, and 2 is going to be pointing in the direction here. And 1, 2, 3, and 4 then are exactly canceling out. So now I have directions, magnetic field directions, 1, 2, 3, and 4, and they're all canceling. So I'm getting perfect cancellation. In this picture, there won't be any magnetic field at the center because the 4 effects from the 4 wires, they're all canceling out. Questions on that? Time to think about. All right, let's look at this example. We talked about this a bit, I think, back in chapter 27, and now we're set up to where we could actually carry out a calculation. If I have 2 charges that are both traveling kind of side by side in the same direction, the magnetic effects on those is actually to draw the 2 charges together. Even though the electric effects, if they're both positive, would repel, the magnetic effects tend to draw it together. Now, an easier way probably to see that is rather than using individual charges, let's use wires with current running through them. So what I've got now is I've got 2 wires, wire 1 and wire 2, and they are carrying current 1 and current 2. So I've got a couple of currents running through these wires. They're separated by some distance d. And what we want to do then is determine whether or not the wires are exerting forces on each other. And it turns out they are. We'll see that. And it turns out that 2 wires, 2 currents traveling in the same direction are going to end up attracting each other. The formula, let's see, so this is their formula for the magnetic field around a wire, and they're using mu naught, that's fine. And then this is the force formula. What they've done is they've combined this formula from chapter 28 and a formula from chapter 27. We'll go back and see how this works. But by combining those two formulas together, they're ending up with a force formula. Now we want to break this down, be really clear about the two steps. So the first thing is, let me see if this works better. So here's a diagram that I drew for this. Now eventually we want to get to that picture where there's two, we want to get to that picture on the right where there's two wires running parallel to each other. But rather than start out with both wires, let me start off with just the one on the left and say that it's going to have a magnetic field given by 2k I1 over c squared 1 over r. So that is, that's the magnetic field due to a long straight wire. Now, we said that each wire had 20 amps in it, I think, or else I put those numbers in, and that the distance between the two wires is 20 centimeters. I think maybe, I'm not sure, I think I put these numbers in. So 20 amps, 20 centimeters, and I didn't plan for this, but it did work out. 20 microtesla is the strength of the field. So the idea is this: I got a wire right here. Before I put that second wire in place, I'm going to do a magnetic field calculation and find out that at every location along here, I am ending up with a magnetic field that's 20 microtesla. So when I move over to this picture, now I'm going to take that wire and bring it into my diagram. Everywhere along here is a magnetic field of 20 microtesla due to wire number 1. So wire number 1 generates a magnetic field everywhere. I decided to put a second wire right here at the 20 centimeter mark. And as a result, I'm going to have a force acting on wire number 2 that depends on its current, its length running through the magnetic field, and it's going to depend on magnetic field 1. So the force acting on wire 2 depends on the magnetic field generated by wire 1. And that's breaking this into two steps. And so if I take this formula to calculate my force, and I notice that there's a B1 in there, what I can do then is I can pick up this B1 formula here, carry it over, and then it'll look like the formula that, let's take a look and see. So before I do that, so the plan here is this: to calculate the force on wire 2, I need to know what the magnetic field is from wire 1, and wire 1's magnetic field is given by this expression. Let's plug that in where B1 is located in my formula. And that's how they're coming up with this combined formula. So it depends on both currents, depends on distance of separation, and it depends on how much length, and then the constants out front. All right. So we were able to calculate a magnetic field of 20 microtesla. And now plugging numbers into here, well, let's get direction, I guess. We want to find out direction first, so let's do that. We said that if the currents go in this direction, then we're going to have magnetic field going into the page on this side, coming out of the page on this side. Into the page is where we're placing wire number 2. And so if I run current in a region where the magnetic field is going into the page, using my force formula, the force is going to be in the direction of I cross magnetic field. And so the force will be this direction. That says wire number 2 gets drawn, it experiences a force, pulling it towards wire number 1. Okay, so that's the directional information. So from the formula we had worked from for magnetic fields, and back in chapter 27, the formula for magnetic forces, we can now see the prediction that two currents of wire number 2 is going to get pulled towards wire number 1. Is that argument reversible? And what I mean is, if I start with wire 2, how would I determine what wire number 1, what force would be acting on wire number 1? Well, let's go back. Instead of saying this picture is wire number 1, what if we said this picture is wire number 2? Now, wire number 2 also has a magnetic field that looks very similar to wire number 1. In this case, where is wire number 1 going to get placed? And if this is wire number 2, wire number 1 gets placed here, where the magnetic field is coming out of the page. And so when we calculate the force that's going to be acting on wire number 1, what we're going to end up with is, oh, this is my left hand. That's why it's backwards. Sorry about that. I got to use my right hand for the right hand rule. So here is the magnetic field coming, or the current, sorry. Current going here, magnetic field coming out of the page, force is going in this direction. Sorry about that. So remember, during the exams, if you get a cross product problem and you're right-handed, put the pencil down first and then use your right hand. Otherwise, if you keep writing, it's probably your left hand you're using. Don't do that. So this diagram is reversible. What it shows is that both wires are going to experience a force. This time it is the same, it's symmetric. And the amount of that force, putting all the numbers in, turns out to be 160 micronewtons. Now, and it's 40 meters of wire. That's a lot of wire that they put in this example. I don't think I would have introduced maybe I did, not sure. Anyway, let's talk a little bit about this angle right here, because remember in our force formula, we've got that cross product going on. So what's happening here is it's the angle between the direction of the current and the orientation of the magnetic field. And so what's happening is the current is here, the current's in this direction, the magnetic field is into the board. That's 90 degrees between those two. And that's why theta is equal to 90 and sine of 90 is 1, and that's how that got dropped. Okay, so it's always good to come back, and you definitely want to be practicing in terms of directions for the forces and for the fields. Want to check those on every problem that you look at. All right, so we do get this attractive force between two wires with current. And again, the force is not just at one location. It's all along here where the force is happening. Now, if we run the currents in opposite directions, what that's telling us then is that there will be a repulsive force. We'll end up with a repulsion between those wires. And you can, I don't have those demonstrations with me, but you can set up wires and put the current through and actually see the wires draw towards each other or the wires push away from each other, which is kind of interesting to do. Here's another problem. You could imagine carrying this out. Two wires, 2 meters long, 3 millimeters apart, current of 8 amps DC. Find out how much force. Now remember, when you're calculating the force here, it's the force that each wire experiences. So see how there's an F on each one of the wires. So I1 gets pulled towards I2, I2 gets pulled towards I1. It's an attractive force that both objects experience. All right, we are ready to, after looking at some of these examples, calculating magnetic fields. Here's another way that we could calculate magnetic fields. It's called Ampere's law, and it's going to kind of remind us of Gauss's law. Remember back in chapter 21, we had determined a very systematic way to calculate the electric field for any charge distribution. And then we went into chapter 22, and said, you know, if there's enough symmetry, we can kind of use this shortcut. But it's really only a shortcut if there's a lot of symmetry. Well, it turns out that in calculating magnetic fields, there's another theorem. There's this Gauss's theorem for electric fields. There's now a Gauss, not a Gauss's law, but Ampere's law, based on Stokes' theorem, that applies to magnetic field paths. And what it says is this. It says that if I follow magnetic field lines along a path, that will always add up to be mu naught times I enclosed. Now, here's a kind of zigzag example. So here's a wire, and I'm following this path, and I'm measuring the magnetic field, and by the time I've closed the path, so again, the integral sign has a little circle in here to say that it needs to be a closed path. So by the time I've completely closed that path, adding up all those magnetic fields needs to be equal to this quantity. Let's look at a simpler example. We can come back and look at the zigzag. Oh, it looks so much nicer. So here, what they've done is they've picked a nice circular path that circles around this wire with current. And so the theorem states this: if I take the magnetic field and multiply it by the path. Now, what we've done here is we've smoothed out the path so that we can now make the argument that if I stay right on a circular path with the same value of R at every location, that will guarantee that the magnetic field will have the very same value everywhere along the path. Now, what I can also say is that since what we've seen is that magnetic fields form loops around these wires, not only is the magnetic field going to be uniform, but everywhere along my nice circular path, the magnetic field is going to be pointing right in the direction of that path. So what that does is, let's look at the left side of this calculation. That's a path integral. I'm integrating a vector field value along a path. If B and DL are pointing in the same direction, then I can drop the vector signs. I don't need the vector signs anymore. I'm going to pick up a factor of cosine of 0 degrees. Cosine of 0 is 1. And so what was a vector calculation has become a scalar calculation. And then since I picked this nice circular path, B is going to have the same value at each location. So I can factor the B out, not factor it out, but bring it outside of the integration. And then all I'm left to do is calculate the length of the path. So remember how with Gauss's law, we said we're only going to use Gauss's law in circumstances where we can say the flux is just E times area. E times area, that's all we need to use. For Ampere's law, it's going to be B times path length. And we'll see different path lengths, but every time we use Ampere's law, it's going to be B times path length. Those are the only times when it's really easy to use. So what happens here then is, Ampere's law says that if I calculate B times path length, B times 2 pi r, it's going to equal mu naught times I. And so we end up with the same formula we had before. We end up with mu naught times I divided by 2 pi r. So this is a shortcut formula for calculating the field around a long wire. So if I have a long wire with current running through it, I can use this as my calculation. Now, this was a nice, smooth integration path. This is a zigzag path. Ampere's law works for both cases, but this would be near impossible to calculate, right? If I pick a path so it zigzags, it's not going to line up with my magnetic field. And if I go to different distances, the magnetic field value won't be uniform. So actually carrying out the integration on the left side would be just horrifying. It would be terrible to have to do that. But Ampere's law says if you did, you would still get this value. So I can pick a path that's closer in, I can pick a path that's farther out, I can pick one that's zigzag, I can pick one that's shaped like a hexagon. Whatever path I pick, it will always give me mu naught times I. But we only want to use that example, we only want to carry out those integrations when there's enough symmetry to make the integration equal just b times path. Okay, and in this example, we get the formula that we had before. So again, just one more drawing, my own personal drawing for this. So I'm going to say Ampere's law, here is my path integral, and see how I'm carrying out the integration. It's b times the length of the path. 2 pi r is the distance all the way around that circular path. Now, rather than using mu naught, I'm going to try and do everything in terms of 4 pi k over c squared I. And so this becomes the enclosed current. And when I solve for what the magnetic field is, what I'm getting is 2ki over c squared 1 over r. And that's, using little k, that is the formula that we got before. So it's a little more stuff to carry around on this side of the equation, but a fair amount of that actually ended up canceling out in any case. So that's it. That's what the formula is based on Ampere's law. Now it's an approximation because the symmetry argument we're using for Ampere's law only works if the wire is infinitely long. If it's a short segment of wire, then I can't guarantee that this path is going to be completely uniform at all locations along the wire. And so again, it's an approximation, assuming that the wire is really, really long. Now what we could do, remember with Gauss's law, when we had introduced Gauss's law, kind of the first thing we did with Gauss's law, was we looked at spheres, and we asked, well, what would happen if we went right inside a sphere of charge? When we were outside the sphere of charge, Gauss's law predicted an electric field that behaved like a point charge. But what would happen if we then went right inside of the sphere? And we found out the electric field would drop off as we got closer and closer to the center. Well, we could consider the same question using Ampere's law. So, and the setup would look something like this. Now, in the previous example, we said we had current running through a wire. We had looked at a location outside of the wire, and we used Gauss's law to determine a formula for the field that was outside. But now we want to look inside the wire itself. What would happen, what would the magnetic field be at a location inside the wire? In fact, we could ask, what would the magnetic field be right at the center? And it seems like the way that the magnetic field forms these circular loops, that the magnetic field at the center wouldn't necessarily go to 0, and that does turn out to be the case. But Ampere's law makes a very specific prediction. It says that if we set up, we had those Gaussian surfaces, these are like Amperian paths. So this was the path, 2 pi r, when we were outside of the wire. But now we can pick a path inside the wire, also 2 pi r, but the difference this time is now the path we're using is less than the radius of the wire itself. whereas before we were outside the wire, now we're inside that copper itself, asking what the magnetic field is going to be. Now the assumption we make here is that the current is uniformly distributed along the wire. So this wire has like a circular cross-section to it, and we're assuming that current is kind of flowing at the same density at all locations across that. And for that, what we find out is that, and we'll look at the derivation on the next page, but what we find is that the magnetic field is 0 at the center, and then linearly increases until you get to the edge, and then it drops off like 1 over r. So again, that's a similar plot to calculating electric fields inside and outside of a sphere using Gauss's law. So a lot of similarity there. We can look at the numbers here. I don't think I ever plugged the numbers in, but it says here that the wire itself is 2 millimeters, and that's your standard 12 gauge wire that I rewired my house with. So 2 millimeters, ooh, 60 amps, that's too much. That'll blow my circuit breakers for sure. And then it says at 1 millimeter, oh, this is R. I take that all back. This is actually not the diameter, it's the radius. So it's actually 4 millimeters. It's much thicker. And it may be just fine. Let's see, it could be just fine because it's got 4 times the cross-sectional area. So it's got 60 amps. So this is like an oven or something, a range. You know, you're using a much wider wire, and you're running a lot more current through it. What is the magnetic field at 1 millimeter? What is it at 2 millimeters, and what is it at 3? So those 1, 2, and 3 are going to take us from a point halfway between the center of the wire and the surface. That would be 1. At 2 millimeters will be right at the surface, and then at 3 millimeters will be outside. So on the graph, it's going to be here, here, and here. So let's see what those calculations look like. It may be we just get part of this set up. I think I might do that. Let me do this. Let me talk just a bit more about this, and then we'll come back and in the next lecture, and we'll start off with this example, because it's a pretty interesting example to look at, I guess. So here's the wire. I drew a different picture. I'm assuming that the current's uniformly distributed through this wire. Here are my paths of integration. I drew one. I figured I should draw one in the middle. I drew one kind of at the end, and then decided to draw another one here. So if I turn this wire and I look at its circular cross-section, here is the circular cross-section of the wire. Apparently that's the center. Sorry about that. Maybe here. So the center should have been over here somewhere. Here is the radius, big R is the radius of the wire itself. That's where the wire is. Now we're looking at path integrations that are either within the wire or outside the wire. And what we want those to do for us is to give us formulas for what's the magnetic field inside a current carrying wire and what's the magnetic field outside. And so for that, here we are outside the wire. That was the easy one. And here is Ampere's law. B times 2 pi r is equal to 4 pi k over c squared I. We did this already, and we got the formula B is equal to 2k over c squared I 1 over r. And that says if I'm outside the wire, that's determining the magnetic field. Now, inside the wire is a little more complicated. Inside the wire, what we have to do with Ampere's law, sorry. Let me go back to where this is written out. The current that we put together in Ampere's law, in the formula, the current that's in that formula has to be the enclosed current. So same thing we saw with Gauss's law. What we have to do then is, if we're going to pick a path of integration to calculate our magnetic field inside the wire, I don't want to include the current traveling in the outside regions. The magnetic field effects from those outer regions are going to cancel out exactly. So I don't need to include those. And so that says that the enclosed current that I want to include is only a fraction of the total current. And that's going to be pi little r squared over pi big R squared. So what I'm doing is I'm looking at that circular cross-section, saying currents coming out from all different regions, and I only want to include the enclosed current, and that's the fraction that I'm going to work from. So side by side, it's nice to see these two formulas develop. The left side of the equation is the same, even though in this side, little r is less than the radius of the wire. I'm sorry, it's bigger, it's outside the wire. Here we're inside. The only difference here is in the enclosed current. When I'm outside the wire, all the current runs through my path of integration. But when I'm inside the wire, the path of integration only includes a portion of the current. And so I had to include this factor. So the formula I get looks the very same with this extra factor attached. Little r squared over big R squared. And I rewrote it in, maybe it's a good way to write it. Now, what would happen at the surface? Because one of the places they had asked us about was what is the magnetic field right at the surface? And it should be that the two formulas will match. And they do. So when I get to the surface, all of the current is enclosed, and now that's represented because this is going to become big R, and this factor will become 1. So now I've enclosed 100% of the current at the surface. And so what will happen then is this becomes big R and cancels out. In my other formula, little r becomes big R, and the two formulas then match up. So if I look at an overall graph, starting from, let's say we start at the center of the wire and step outwards. Now we know that we're going to get that right hand, we know the direction here. The direction of the magnetic field is going to be those right-handed loops. And this is going to tell me how large the magnitude is. So, and that magnitude is going to increase linearly according to that formula. That's the formula for a straight line. The only variable there is little r. So it's b as a function of little r. And then the functional dependence here is 1 over r. So that's the formulas that we're going to end up with. So that's a good place to wrap up. I think maybe we're just right on time. Maybe we're a bit over. So probably next lecture we'll come back. We'll look at this as maybe a jumping off point for using Ampere's law. And then we'll look at there's a couple other examples where we use Ampere's law to give us some very useful formulas for calculating magnetic fields.